All right. So I'm going to be talking about FFT, and what's going to happen today is that I'm going to be explaining the mechanics of FFT from two perspectives. One that you have seen thoroughly in lectures, so from two perspectives talking about FFT. One perspective that you've seen thoroughly in lectures, which will be the matrix perspective. I will not dive into the extreme details of that because you have lecture recordings, and we also have some videos that Professor Vaziani recorded in 2013 that we found. So we'll release those for that perspective. I'm going to talk about the polynomial perspective, which is an alternate perspective that helps students see what's actually going on, what the algorithm under the hood is. Is there a question? Okay, no question, just waving. All right, so let's get started. This slide sucks. Okay, I promise you the other slides are not like this. But the ultimate goal of FFT is multiplying polynomials. And I know this is not visible, but essentially these are two polynomials of degree 7 and 8. And the idea here is that if you start with two polynomials, each with 3 terms, you end up with a polynomial with 9 terms, right? And you all have seen this, you've been doing this since high school. You have two polynomials like x squared plus 2, you multiply that with like x plus 4, you have 4 terms because you need to cross multiply every term. That's n squared terms. That's no good. We want to do better. Doing better takes about an hour. So we're going to do better in an hour. And let's see what clever things we can do with complex numbers that help us do better. So few facts. This should be review. A polynomial of degree d is uniquely determined by d plus 1 evaluations. If you've forgotten this, here's how I like to remember it. A line is a polynomial of degree 1. It's like x plus 3 or something like that. That's uniquely determined just by 2 points, right? So degree 1 determined by 2 points, and just extrapolate. So this is from CS170. This should be review. This is a quick fact. So essentially we could represent a polynomial of the form ax cubed plus bx squared plus cx plus d in its coefficient form. So this is sort of, we can write it as a vector, which is dcba. You've seen vectors written as columns. For the sake of space, this is written as a row, but you should be writing it as a column, okay? So don't get confused by that. Okay, so or we could evaluate this polynomial on d plus 1, which is in this case 4, because the degree is 3, on 4 points. Let's say that the points we want to evaluate it on are 1, 2, 3, and 4. And in that representation, this polynomial would look like this. Can everyone see the bottom line in the back? It's clear? Okay, cool. So in that representation, this polynomial would look something like this. You would have a vector of 4 elements, p evaluated at 1, p evaluated at 2, p evaluated at 3, and p evaluated at 4. So when we evaluate p at 1, we get a plus b plus c plus d, 8a plus 4b plus 2c plus d, and so on. This representation is the value form representation, and it's inbuilt. It has 4 points, 1, 2, 3, 4. It's the value form representation on those 4 points. And this is the coefficient representation. So since, this slide says that a polynomial of degree d is uniquely determined by d plus 1 evaluations, that means that these two are basically equivalent, right? We can either represent it in its coefficient form, which is a unique way to represent a polynomial, or we can represent it in its value form, which also is a unique way to represent a polynomial. Any questions so far? Okay. So next, here's a fact 2, which is that multiplication in value form takes O of n time. So remember how we had this whole thing about how if we have a polynomial multiplying another polynomial, that takes n squared time? Not in value form. Let's see why. So say that there are two polynomials, p of x and q of x, each is of degree 2. So if you guys are writing notes, these slides will be posted and they might be a little too fast for you to write notes. You're free to, but I would suggest just sort of listening and sit back and relax and have a good journey. All right, this is a... All right. Okay, so say that there are two polynomials, p of x and q of x, each of degree 2. And what we want to do, so be careful, we want to find the value form of r of x, which is equal to p of x times q of x. So r of x is a polynomial, which is multiplying these two polynomials, and we want to find its value form. First, r of x needs at least 5 points. Why? Yes?
Because multiplying the two polynomials will give you a degree 4, so you need 5 points.
Good. So multiplying these two polynomials, each of degree 2, will give you a degree 4 polynomial. And to represent that degree 4 polynomial, we need 5 points. Yes? Okay, good. So R of x equals P of x, Q of x will be of degree 4, needs at least 5 points. This is exactly what I said. So let's build this up, right? You know how you write a math proof, it says given, to prove, blah, blah, blah. Well, it's useful. So given, what are we given? Let's say that you have P of 1, P of 2, as in you have the polynomial P and the polynomial Q in value form. So let's say you're given this. You're given the value form representations of both of the polynomials, okay? What you want to find is R of 1, R of 2, because this is the value form representation of R. That's our goal here. Okay, very small mini little goal, which we'll plug into our FFT algorithm soon. But for now, this is our entire goal. Okay, how do you do this in linear time? Well, R of 1 is nothing but P of 1 times Q of 1. Easy, right? Why? Because just take a look at this, right? Plug in 1. R of 1 is P of 1 times Q of 1. What is R of 2? P of 2 times Q of 2. R of 3, R of 4, R of 5. Linear time, just 5 multiplications. That's it. Question so far? You believe me? Okay, good. Okay. Sorry, I don't know what happened. Okay, all right. So the conclusion now. So all of my slides are based something like this. They have a lot of conclusions, and you should keep them in the back of your mind, but I'll remind you as we need them. So our conclusion here is, given the value form representation of P of x and Q of x, we can find the value form representation of their product in O of n time. That's the conclusion. Conclusion sort of number 1 of the day, okay? All right, good. Next, now we need to worry about, well, usually when we have polynomials, they're given to us in coefficient form. So far we were in this dreamland where we started in value form, but we need to get to value form, right? And unless and until we can get to value form fast, this whole thing is a waste. So let's see how to get to value form fast. Okay, say that we want to evaluate this polynomial, d plus cx plus bx squared plus ax cubed, on these 4 points, 2, 3, 4, 5. One way to think about evaluation, of course, you've seen in high school, just, take this polynomial, plug in 2, plug in 3, plug in 4, plug in 5. That gives you your evaluations. That's one way. Another way is by representing it in matrix vector form. And this is going to be useful. That's why we're doing it, obviously. So let's see how it's going to be useful. So I want someone to volunteer and tell me what should go in the first row if I want to evaluate this polynomial at 2. Come on. Otherwise, we're wasting time. Come on. Yes, in the back. So what goes here? Okay, so this is going to be 1. That's why I wrote the polynomial this way. So it's going to be 1, 2, 4, 8 was the answer. So let's take a look at why. So this is the answer more formally. It's 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3. Why? Let's take a look. This is exactly what's going on, right? 2 raised to the power 0 should be hitting D. 2 raised to the power 1 should be hitting C, 2 raised to the power 2 should be hitting B, 2 raised to the power 3 should be hitting A. This is exactly the same thing as evaluating this polynomial. Are you convinced that matrix vector multiplication, if we choose the matrix correctly, of course, can give us the value form representation of the polynomial, given the coefficient form? Convinced? I need some nods, then only I know that you're convinced. All right, I got some nods. Yes, you had a question. Okay, no question yet. All right. And similarly, if you want to evaluate at 3, same thing, right? 3 to the power 0, 3 to the power 1. We're seeing a nice pattern here, and it's going to be useful. So let's remember this pattern, engrave it into your head. It's going to be useful forever. Okay. And so on, right? Basically, you can convert any polynomial in coefficient form to value form by multiplying by a matrix, and the matrix depends on the points. Important, matrix depends on the points. You can't plug this matrix for whatever points, right? Okay. Any questions? Okay. But this takes O of n squared time. Why is that? All right. Yes?
You have that many multiplications.
Right, you have that many multiplications, right? This matrix itself is of size n squared. So you need to do sort of 1 multiplication, 2 multiplication, 3, and n squared multiplications. So this isn't speed up at all. This is completely useless, right? We can do naive polynomial multiplication in n squared time. So far, we've achieved nothing. Okay? But we'll get to it. What have we learned here? That you can go from coefficient form to value form by multiplying by a matrix. That's all we've learned so far. We haven't achieved any runtime speed up. Okay? With me? Cool. I know it's late, but stay with me. I'll try to be entertaining. All right. So, putting the fast in FFT, right? This is an important step. We haven't done this at all. Let's do it now. But to do that, we need some complex numbers background, so I'll bring you all to the same page, and hopefully this should be everything you need to sort of follow what's going on. Complex numbers are numbers that look like a plus bi. What is I? I is the square root of -1. Okay? You may have seen in grade 7, square root of -1 is just like whatever, not defined, but this is what it is, right? I is the square root of -1. Complex numbers can also be written as e to the power I theta. Oh, I messed up. Okay, so let's look at this slide instead. So complex numbers can also be written as r e to the power I theta. Okay, and you can expand this out. So there's this wonderful identity called Euler's identity, I think. I don't know. Okay, it's r cosine theta plus I r sine theta. Okay, these are the two representations of complex numbers, widely accepted. Maybe more. I don't know. I haven't taken enough math. Okay. To convert between the two, it's pretty straightforward because you have two equations. A is r cosine theta, right? Just match, pattern matching. And B is r sine theta. Two equations, two variables, right? Because either you're given r and theta or you're given A and B. And just solve for r and theta if you want to go from one form to another. Does that make sense? How do you do that? Well, just if you want to find theta, divide A by B, you get tan theta or 1 over tan theta, then you do tan inverse. So it's a whole thing, it's messy, we probably won't ask you to do it. But if we do, be prepared. How do you find r? Well, after you know theta, you can find r, right? So that's how you just find these. Okay, questions? Okay. Now, these complex numbers, I don't know if you guys can see. Let me zoom in. How's that? Better? Not that good? Okay. I'm sorry, but let me try to follow my mouse to it. So this is the complex number representation in polar form. This is how you can draw it out, right? This is the y-axis, this is the x-axis. We use the x-axis for the real part. We use the y-axis for the imaginary part. And in this form, angle, so remember there's a theta. This is theta. I couldn't draw theta, but this is theta. And this is r. So the length of this vector is r, and the angle from the origin, from the x-axis, is theta. That's one representation. Equivalent representation is a plus bi, which is just the Cartesian coordinates a comma b. So a on the real line and b on the imaginary line. Okay? Why am I talking about this? It will be important, I promise you. So stay with me. Okay, questions? Okay, good. All right. So now let's talk about the roots of unity. This is sort of the second step into talking about putting the fast in FFT. What are the fourth roots of 1? Some of you might say just 1 and minus 1. That's not true. There are 4 roots of 1, right? There's 1 to the power 4 gives you 1. Negative 1 to the power 4 gives you 1. But also I to the power 4 gives you 1. Why? Because remember what I squared was? I squared was negative 1. Or rather, the way I said it earlier was that I is the square root of negative 1. So I squared is negative 1, right? So what I'm doing here is I squared squared, which is negative 1 squared, which is 1. There's another one, which is minus I. Take minus i's like this. Take all the minuses out of that. You get I to the power 4, which is also 1. So there are 4 roots of 1 if you allow for complex numbers. And this is going to be really important. So this is what FFT is built off of. The fact that you get more and more roots, and they're somehow related. We'll see how they're related, but they're somehow related. Okay? And similarly, there are 8th roots, 16th roots, 3rd roots, 7th roots, whatever you want. How many ever you want. And I'll show you a general formula for how to get them. Okay, I think that's on the next slide. Okay. If you notice, this is why the geometric part was important. If you notice here, the 4 roots of unity, this is, okay, so let me explain this diagram. This is a circle of radius 1. Okay? And these 4 roots lie here. So remember a plus bi, that representation? Well, 1 is obviously going to lie here because it doesn't have anything on the complex numbers. I is going to be here because it doesn't have anything on the real numbers. Minus I is going to be here, minus 1 is going to be here. So you see how they beautifully distribute along the circle, like evenly spaced? You have 1, I, negative 1, and negative I. This is a fundamental property of the roots of unity. If you had the 3rd roots, they would evenly space out. We have 360 degrees to distribute. The 3rd roots would take 120 each. So the first one would be sort of somewhere here. The second one would be somewhere here. And that's it. It would form like a nice, like, I can't do that. Okay. That makes sense? Yeah, something like that. I don't know. Okay? Cool. So now the next natural question to ask is, well, you told me what the fourth roots are, but what are the nth roots, right? We keep talking about the nth roots of unity in this course. So the nth roots of unity are actually given by this amazing formula. It's e to the power I 2 pi k over n. Show you an example because this is sort of confusing. What are the eighth roots of 1? For n, you plug in 8. So n remains constant when you're finding the roots for that number. And sorry, k is the indexing variable. So this is sort of the 0th root, 0th eighth root of n, the first eighth root of n, the second eighth root of n, the seventh eighth root of n. This is how it goes. Make sense? General formula. Okay. All right. And here's a nice, let's zoom in. Okay. Nice little GIF. So they evenly space out. Let's wait for it to restart. Come on. Okay. 1, then 2, then 3, then 4, and so on. They always evenly space out. This is a wonderful property of the roots of unity. You can try to prove this at home. It'll be a fun exercise. Yeah, try it out. Try out why this is the case. But you have to learn how to take the square root of complex numbers. It'll be fun. Okay. All right. Moving on then. Now let's talk about what happens when we square the roots of unity. So far I've talked about, the first thing was complex numbers, then I talked about the roots of unity, now I'm talking about squaring the roots of unity. So we're building up to FFT, bit by bit. Okay. So, oh yeah, quick note, for the roots of unity, R is 1, remember our representations, R e to the power I theta, so R is 1 for the roots of unity, their radius is always 1, and they all lie on a circle of radius 1, that's basically what this means. Now let's think about what happens when we square the roots of unity. So e to the power I theta squared is e to the power I 2 theta, right? So what's happening? Well, notice how the number outside here, even if it was like a or, you know, well, no, if it was a, it would change. But since the number outside here is 1, right? R is 1, right? R here is 1. There's an inherent 1 here that's not written out on the slides. When we take the whole square of that representation, all that happens in this case is the angle gets doubled. That's it. That's all that happens, right? So let's take a look at what that means. When you have 1, right, this is the original root, the fourth root. I'm going to square this. I'm going to fall right back here, right? The angle was 0, still 0, yes? Next, the angle is 90. What's going to happen to the angle? Come on, 180. See it? Can you see the line? Yeah, I think you can see it. It's green. Okay. So the angle becomes 180. What happens if you start at 180? The angle becomes 360, right? So it goes back all the way around. What if you start, this is just bad. Okay. If you start down here, okay, so this one is you're starting at an angle of that's 3 quadrants away, 1 quadrant, second quadrant, third quadrant. So doubling this angle means, well, just loop around 3 more times. So 1, 2, 3, you land here. Okay? Everyone see that? So essentially to visualize this, just imagine doubling the angle. Just double the angle, that's it. Right? Squaring them, double the angle, that's it. Okay, I'm actually not going to do this in too much detail, but this is the 8th roots. If I square this one, so this one, you see how I land on I, right? The angle just doubles. I square this one, I land here. I square I land on -1, and so on, right? Okay, so this is the squaring the roots of unity part. This can be helpful in some problems if you're able to do this instantly. If someone asks you, well, what are the 8th roots of unity, and you can visualize it in your head. These answers that I wrote out here, I just wrote out by thinking about it because they have to be evenly spread out. That means what is the sort of distance here? Use Pythagoras theorem in your head. And you can sort of get this out, right? So doing this sort of visualization helps you get faster at things, and it's also crucial in one next observation. Yes.
So in our homework and discussion, I don't believe we ever use that indexing term, 2 pi k. Correct me if I'm wrong, but like, where does that? If we haven't seen that before, where does that come in?
So you're saying that you haven't seen this in homework or discussion? The K, okay, so I'm pretty sure it's in this week's homework, I think. So that's one, right? It'll help you in this week's homework. All right. And apart from that, this should be in the textbook too. So I don't know if it was explicitly said in lecture or not, but you know, you've been seeing omega everywhere, right? This is essentially omega. I'll talk about that later, but this is essentially omega. This is the expanded form of omega. Okay? Okay, I'm hearing some restlessness. Are there questions? Yes? So the question is, do you just use a K so that the math would be nicer? Well, not exactly. Actually, so, you know, how do I put this? Not exactly. There's no sort of easier way to write this out. This is the most compact way to write out the nth roots of unity. Right? This is just, you write it out like this, and if you plug in 8 here, and you say that K goes from 0 to 7, that sort of generates all the 8th roots of unities. Did I get the question right?
No, I'm saying like, okay, so all the elements have to do with like 2 pi over n and being like whatever root of unity is involved. And then once like, it's kind of like weird to equal sometimes, like in, so does adding the k, they're just like, it's there, like the size or like.
Okay, I see. So I think the question is about this n, where to put it. Sure, you can write this as e raised to I 2 pi over n as its own thing times k. That's the same thing as this, right? There's no difference. The effect of k. Are you talking about this k? Okay. So how do I answer this? So this, okay, let's take a look at this number in particular, right? What is this equal to? This is just e to the power I times 0, right? Which is e to the power 0, right? So this is 1, correct? Anything to the power 0 is 1, right? Okay. Now, if you were to evaluate this, or if you were to evaluate the next one, let's evaluate this, right? So this is e to the power I, what is it? 4 pi over 8, so e to the power I pi over 2, right? So this is going to evaluate to 1. How is that going to happen? So this is, remember, e to the power I pi over 2, so the angle is 90 degrees. And let's go back here. Angle is 90 degrees, right? So we get cosine of 90, which is cosine 90 degrees, 0. Plus I sine 90 degrees, 1, right? So I get I, that's my next root, and so on. This is just an easy way to generate the roots. It's just an easy way to remember what the roots are. This simple formula gives you all the roots. If you have questions, we can talk later, maybe more, okay? More questions? Okay, cool. So this was the demo part. Let's move on from here. Oh yeah, also, these angles they're 2 pi periodic. What does that mean? That means that, okay, simple idea, right? If you're at angle 0, so this is the angle 0 on that circle, right? Versus if you're at angle 2 pi. Does that make any difference? No. So all of these angles are 2 pi periodic. You can add or subtract 2 pi freely, right? The angle 90 degree for all of our purposes is the same as 90 plus 360. Does that make sense? So all of these angles are 2 pi periodic. We are in this sort of periodic signal, which just repeats itself every 2 pi. Okay. Okay. So just a quick side. Okay. So the conclusion that I wanted you to get out of the demo is that when you square the nth roots of unity, you get the n over 2th roots of unity. So what does this mean? Now let me go back here. So these are the 8th roots of unity, right? You can convince yourself either visually or by mathematically working it out that when you square all of these roots, right, you will get either 1, I, minus 1 or minus I. You will not get something that's sort of in the middle here. Why is that? Can someone sort of give me a convincing argument from this image as to why that is? As to why if you square a root, you will never lie back on one of those? Yes?
So it's like, that seems like an odd number and it's an even number and you multiply by 2. You never ever lie. Yeah, even if even, you never go odd. If it's odd, you never go even.
Good. So the argument is of even odd numbers. When you multiply an even number by 2, you get an even number. When you multiply an odd number by 2, you get an even number, right? So why is that relevant? Well, let's just look at the number of quadrants away that we are, okay? If you're sort of an odd number of quadrants away, then you're going to be 2 times an odd number of quadrants away, which is an even number of quadrants away. If you're an even number of quadrants away, then you're going to be 2 times that away, which is still even. So all you're going to end up with are even quadrants, which are the 4th roots. Does that make sense? Convincing enough? Not convincing? Questions? Okay, so squaring the nth roots of unity gives you the n over 2th roots of unity. And this will help us speed up the process of transforming from coefficient form to value form. This is the sort of the crux of FFT. Let's see how. So we have to do some did I miss a slide? I did. Okay, no worries. Okay, so let's first write, let's go back to our polynomial view of things. So now we're coming back, okay? We've talked about complex numbers, we've talked about some things. Our conclusion, final conclusion was that when you square the nth roots, you get the n over 2th roots, okay? Now we're coming back, let's come back. We write p of x as ax cubed plus bx squared plus cx plus d. What I'm going to do, some cleverness, I'm going to break this polynomial apart into 2 polynomials. I'm going to do this. P of x is b of x squared plus d plus x times a of x squared plus c. Any questions so far about this? Okay, now you notice how this green thing is a polynomial of its own. It's a polynomial in x squared, ae of x squared. This is very important. I'm going to say it again, ae of x squared, not ae of x. I've seen way too many students make this mistake. So again, ae of x squared, I'll talk about this in 1 second, plus x times ao of x squared. So quick pop quiz, the answer is already here, I'm sorry. But the question was, what is ae of 2? So this is ae, remember. ae of 2 is 2b plus d, not 4b plus d. This is like the most common mistake I have seen students make. Just because you are used to seeing polynomials written as p of x equals something, that does not mean that whatever number you're given as an input is x. In this case, it's actually x squared. We are saying that if I plug in 2 in the place of x squared, then what's going to go here? It's going to be 2, not 2 squared. There are questions about this? If there are, this is the best time to ask. Yes? I'll repeat this. So ae of x squared, right? Now my question to you is, what is ae of 2? Is it 2b plus d or is it 4b plus d? ae is this polynomial. It's actually just if you plug in 2, it's going to be 2b plus d, because you take the x squared and you plug it in as is. You don't square it again. Make sense? More questions? Okay, so this is really important. Make sure you get this right. Okay. Now let's move on. Let's say we want to evaluate p of x. Remember earlier we were doing some silly things like evaluating it at the points 2, 3, 4, 5. Forget about that. Let's now choose our points cleverly. This is the thing that makes FFT fast. Let's evaluate it at these 4 points instead. Let's evaluate it at 1, I, minus 1, and minus I. And let's see what happens. So the whole thing is worked out here. Let me zoom in. This is sort of important. Actually, let's keep it zoomed out so we can see both. Okay. So P of 1, I'm gonna continue this from here. Okay. P of 1 is AE of 1 squared, because this is x squared. Okay. This is x squared. Plus, take x as is plus 1 times AO of 1 squared. Questions on the first line? Okay. The next one is going to be P of I, in which case I'm going to plug in AE I squared plus I AO I squared, and so on and so forth. So I write this for all 4. But you see what's happening? These are the 4th roots of unity, right? These 4 blue ones are the 4th roots of unity. And I'm squaring them inside here. When I square them, what do I get? When I square the 4th roots of unity, what roots of unity do I get? The second roots. Watch. Aha. When we simplify this, we get AE of 1, A of 1, AE of minus 1, A of minus 1, and then repeat it. Repeat it. So this is the magical moment. This is the aha moment. This is where you should be having it. If you're not, just step back, ask me questions. You should have the aha moment now. Because this is the part where we are reusing work. We will recursively call, our algorithm on these polynomials, but we are able to reuse some of the computation. We are able to, we evaluate AE of 1 once, but we use it twice. That's the magic. That's what shaves off a lot of things. We'll see. I'll talk in more detail, but so far, any questions? Yes?
Sorry, can you do that one more time?
Okay, I do that one more time. All right. So P of 1, right? Remember, this is P of x, right? So take this equation, plug in 1 in place of x, right? What happens? P of 1 is AE of 1 squared plus 1 times AO of 1 squared. That's this line. Agreed? Okay. I'm going to plug in I next in place of x. P of I is AE of I squared plus I times AO of I squared. Yes? And similarly the next two equations. But these are the fourth roots of unity. And now I'm squaring them inside here. Squaring the fourth roots gives me the second roots. And that's exactly what happens on the next slide. All of a sudden, I've gotten rid of the sort of i's and minus i's in here. I have them outside here, but I've gotten rid of them inside. This is the magical part. Okay? How are we doing on time? Someone tell me the time. 43. 43. All right, pretty good. Okay, good. So, now, let's think about this. Our original problem was that we wanted to evaluate one polynomial, P of x, of degree d, let's say, and we wanted to evaluate this polynomial at 4 points. So we had one polynomial of degree d at 4 points. That was our goal. What have we done now? Now we want to evaluate two polynomials. Which two polynomials? AE and AO. At 2 points each. What are the 2 points? 1 and minus 1. That's it. We can keep reusing that. And each of these polynomials is of degree d over 2. Okay, the reason I stop is because this should be like, what? Why? So, why do I say, so notice here, right? This was AE, and this was sort of AO. All I'm really going to be doing is taking off 1x. Imagine that this is like a degree 100 polynomial, okay? And what am I going to do here? This is still going to be a degree 100 polynomial, right? Roughly, because the highest order term is going to stay here, right? The x to the power 100 is going to stay here. It's an even term, yes? And here, I'm going to take out 1x. So I'm going to have a degree 99 polynomial here. But I just said that doing this halves the degree. Look at this. What did I say? Evaluate two polynomials at 2 points each of degree d over 2. But that doesn't seem to be what's going on, right? We just seem to be actually not losing any degree at all. So what's happening? Yes?
We're using x squared as so our degree.
Good. So we are using x squared instead of x. And that's what halves our degree. Why is that? Let's take a look. So I actually have that here. Okay. So we have p of x is bx squared plus d. This is the polynomial, right? This is what we left off at. Now remember, this is ae of x squared, and this is ao of x squared. Let's replace this variable. Let's call x squared y. We can do this, right? Simple change of variables, not a problem. Just write it as this, ae of y plus x times ao of y. No problems here, right? And then what does this polynomial become? by plus d plus x, which comes from this, times ay plus c. Do you see what's happening? Now these are polynomials of half the degree. They will be. They've lost half their degree just by the fact that we substituted x squared as y. Questions? Yes?
Can you explain your comment about rounding down?
Okay, so the reason, this is an off by one thing. So let me explain my comment about rounding down. And the reason that comes is because, okay, so p of x was a degree 3 polynomial, correct? And our new polynomials are degree 1 polynomials, right? Take a look at this. This is a degree 1 polynomial,
Okay.
right? So well, this was degree 3. So if 3 is equal to d, then d over 2 is 1.5. Let's just round down. This is an off by 1 error. like a classic standard off by 1 error. And to get rid of that, we just round down. So this is not a big deal. If P of x was degree like 99, right, then you would have two polynomials of degree 99 over 2 plus 1, which would be like 49. No, round down, 48 each. Right, that's what would happen, just an off by 1. Yes?
So I'm still quite unsure on why you're actually making x squared, y equals x squared. Does it actually achieve anything?
Does it actually?
Achieve anything?
So actually, this is purely for thought experiments, right? We don't actually need to do this, but all I'm trying to convince you is that AE and AO are of degree half that of P. That's what I'm trying to convince you. And to convince you, I'm doing this replacement because then it's very easy to see. Does that make sense? But you don't actually need to do this. Computers don't actually need to do this. They can just take the x and square it and plug it in. This is a convincing, this is just purely for convincing you. Okay? Questions? Okay, cool. Moving on then. So, again, our original problem, evaluate one polynomial at 4 points of degree d. Our new problem, evaluate two polynomials at 2 points each of degree d over 2. Great. And now let's talk about the conversion step. So this is the, we don't have it here, but this is the conquer step of divide and conquer, right? We've divided the problem. Let's conquer it. How do we conquer it? Well, conquering it essentially means you have all of these green and orange subresults, right? So your recursion has given you all of these green and orange things. And then it's just sort of 4 multiplications, right? So it's like n multiplications of like real numbers, that's it, or of complex numbers. Does that make sense? So our recursive step, this is the recursion part. We called FFT on this, we called FFT on this. Recursively, we got our answers. That's the T part. So if you have a recurrent solution, I'll have that up now, but if you have the Tn equals 2Tn over 2, then that's all of that takes care of the green and orange stuff. And then the plus O of what is the combination part, right? And that's just linear because we do 4 multiplications, that's it. Questions? Okay, let me show that up on the slides if there are any questions. This is, again, T of n because we started with a problem of size n. Let's say this problem had size n. We broke that up into 2 smaller problems, each of size n over 2. Because now we have half the degree polynomials, and we're evaluating them at half the points. So this is strictly like the problem size is reduced by 2. And then we're doing O of n work to recombine them. It's just a linear number of multiplications. That's it. Questions? Okay, all right, cool. Either I did a really good job or I did a really bad job. That's okay. So, what is our picture so far? Given 2 polynomials P of x and Q of x, we want to find R of x equals P of x, Q of x. What have we done? We have gone from coefficient to value representation for both P of x and Q of x in n log n time. That was this whole thing, right? We evaluated, that was the goal. We want to evaluate a polynomial at 4 points. We did all of this in n log n time. Agreed? So if, again, going back to our ultimate goal, remember, ultimate goal was matrix multiplication, was polynomial multiplication. We haven't gotten there yet. All we've done so far is we've taken P of x from coefficient form to value form. We're done with that. And similarly, we've taken Q of x from coefficient form to value form. Agreed? Yes? Okay. And then we saw right at the beginning, this was our little first conclusion, that you can multiply 2 polynomials in value form in O of n time. Remember that? Okay. So we have 2 polynomials, P of x, Q of x. Move them to value form, takes n log n time each. So far, like 2n log n, right? Multiply them here, takes O of n time. So 2n log n plus n. It's fine. So far, so good. But this value representation is not where we want our polynomial. Right? We want it back. We want it in the coefficient representation. Right? So that's the last step. Inverse FFT. Inverting FFT. Going back from value to coefficient form. Okay? All right. Are you ready? Another roller coaster? Mini roller coaster inside a big roller coaster. All right. So I want to take a step back and talk about the 2 perspectives that we've been sort of going back and forth on. Remember, we talked for a little bit about the matrix vector perspective. Right? We saw that you can just multiply by a matrix, and that takes you to the value form. Right? We saw that that's possible. You saw that if we do that naively, then that's O of n squared, and that's really like no good. right? But you can do that cleverly too in the matrix vector form, and this is what you've seen a lot in lecture. This is something that we'll be posting a video about also. So you like that you should know, like someone wakes you at 4 a.m. you should be able to do that, right? That's the standard, right? So that you should know for sure. And now we talked about the polynomial perspective. How do we see this whole thing as taking a polynomial and just evaluating a polynomial, like straight up? Okay? So there are two perspectives here. Both of these perspectives are doing the same thing. What I showed you is the polynomial fast perspective. What I also showed you was the matrix naive perspective, right, which is just the dumb O of n squared way. What you saw in lecture is the matrix awesome perspective, and it's also in the textbook, and we'll also be posting a video. So like, just make sure you understand that. And now let's take like a few steps back and go back to the matrix naive perspective, because I want to build up something. I want to build up inverse FFT. And inverse FFT is really very easily done in matrix perspective. So let's go back to that perspective. Okay, everyone with me about what the heck is going on? What are these two perspectives? Okay, so it's the same thing. It's just different ways to see it. Okay? Let's go back to this form. Remember, this is the slide from earlier. Good old, we just saw this like 20, 30 minutes back. Okay? Just evaluating a polynomial at the points 2, 3, 4, 5. But remember, we now want to evaluate them actually at 1i, minus 1, and minus I, right? That's what we want to do. We know that that's somehow faster, right? We can do that in a fast manner. That's what we know. So I added these lines just so that we don't get confused. This is not the matrix for I minus 1, I minus I, blah, blah, blah. This is for 2, 3, 4, 5. So I added these lines. Now, let's define some shorthand. So this is some useful shorthand. Omega to the power a is going to be defined as e to the power I, 2 pi a over n. Make sense? So this is the sort of nth roots of unity thing. Earlier you saw this on the slide with a as k. Now we're defining it with a. Okay? And there's this other thing. If n, so in this case, how do you know what n is? Which root of unity are you talking about? Because omega can be used to represent second roots, fourth roots, eighth roots, 100th roots, who knows, right? So if n is not clear from the context, if which roots you're using is not clear from the context, put it as a subscript right here, so 8, 4, whatever. But sometimes it's clear. If you put it in a matrix, it's clear. If it's an n by n size matrix, then n is what you're using, so it's clear. Then we skip it, right? We're very lazy. We don't want to keep writing things. Okay? Cool. So this is just shorthand. Now let's fill this matrix up for these 4 points. First, let's recognize that the fourth roots of unity, these are the fourth roots of unity. These are the fourth roots of unity. Equivalent representation. Okay? Because this is e to the power blah 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 k0, e to the power blah 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 k1, e to the power blah 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 k2, and so on. Right? So these two representations are equivalent. Now let's fill this matrix up. Remember, when you had 2, 3, 4, 5, we filled it up with this pattern. Let's do the same pattern thing again. Ta-da! This was painful, but ta-da! Okay. So omega to the power 0, the first root, power 0. Omega to the 0, power 1. Omega to the 0, power 2. Omega to the 0, power 3. Omega to the 1, power 0. 1, 2, 3. Omega to the 2, power 0. 1, 2, 3, and so on. Right? Okay. Next slide, we're going to make this simpler. Ta-da! All right. You just sort of multiply the exponents out. And you get this beautiful looking form, right? 0, 0, 0, 0, 0, 1, 2, 3, 0, 2, 4, 6, 0, 3, 6, 9. And let's read it up to down, top to down. 0, 0, 0, 0, 0, 1, 2, 3, 0, 2, 4, 6, 0, 3, 6, 9. What a beautiful matrix. All right. Okay. So the explicit formula for this matrix is that its ijth entry is nothing but omega to the power ij. And I and j have to be 0 index because otherwise you don't get these zeros. Yeah? Okay? Cool. So computing the, I want to make 2 quick points, which is that computing the when we have homework problems say compute the FFT of this polynomial. All that means is evaluate the polynomial at the roots of unity, at the appropriate number of the roots of unity. If the polynomial is of degree 6, then just evaluate it at the sort of 7th or 8th roots of unity. Just always round up to the power of 2, because the FFT algorithm falls out beautifully from there, right? Round it up to the power of 2. Okay? So you can do it however you want. And if we tell you to run the FFT algorithm, right, like actually show us all the steps, then you can either do this polynomial thing that I did, where you write it as AE, AO, and go on, or you can do the matrix vector view, which you've seen in lecture. If, and I know many of you will be in this boat because I know how we work, right? I'm a student too. If you are falling behind on that matrix vector view, haven't watched lectures, just don't know what's going on, make sure you catch up to those. It's like super important. That's the view that was covered in lecture, and like you need to know that also. Okay? Cool. So this is the sort of matrix vector view of FFT, right? Still, if we do this naively, this is still O of n squared. So you still cannot do this matrix vector multiplication naively. You still have to be clever, but there are ways to be clever. And that was covered in lecture, again. Okay, how are we doing on time? Who's going to tell me the time? 58, okay. Let's rush through this, or you guys can stay. It's up to you, okay. So, quick note, if you do this naively, it's still no good. I'm going to try to get done by like 05, so if you want to stay till then, all right. Now, this matrix is orthogonal. I knew I would run out of time, that's why I said proof for you at home. I did this beforehand. So this matrix is orthogonal. What does orthogonal mean? Someone quickly. Come on. Okay, so let me consolidate those thoughts. This is a column, this is a column. If you take that dot product, it will be 0. If you take the dot product of any two vectors that are not the same, you get 0. If you take the dot product of a vector with itself, you get some number. You get some non-zero number. Okay? So proof right out at home. I think actually the homework makes you do this week. So you'll be doing it at home anyway. You know, have some fun. All right. Now, quick aside, complex conjugates and inverses. So the complex conjugate of a plus bi is a minus bi. Straightforward, just replace this plus with a minus. Ooh. The complex conjugate of e to the power minus I theta, e to the power I theta is e to the power minus I theta. The complex conjugate of omega to the power a is omega to the power minus a. Right? So just sort of put minuses in some places. That's the complex conjugate of a complex number. Okay? Now, another fact for you from linear algebra, and I encourage you, if you're not familiar with these, Stack Overflow it, and there'll be some nice answers, or buy a math textbook, spend 3 years reading it. It's up to you. So the inverse of a real orthonormal matrix. Okay, what is an orthonormal matrix? I talked about orthogonal. What is orthonormal? Yes. Good. So this means that if you take the dot product of a column with itself, remember how I said you get a non-zero number? In this case, you get 1. Not a non-zero number, but just always 1. Okay, so special, another added property. The inverse of a complex orthonormal matrix is its conjugate transpose. What is the conjugate transpose? The conjugate transpose is, take the transpose, so take your matrix, transpose it, and then replace every entry in the matrix with its complex conjugate. Okay? So if you have a matrix that looks like 1, 1, I, transpose it, then you get, what do you get? Well, I should have thought about this. I1, I think. But replace that. Make it minus I, 1, 1. And that's the complex conjugate of a matrix. The inverse of a complex orthonormal matrix is its conjugate transpose. These are facts from linear algebra. Okay? So I said that this matrix is orthogonal. But so far we've talked about some facts about orthonormal matrices. So let's normalize this matrix. Another exercise for you at home. Go home. Multiply this vector with itself. Multiply this vector with itself. This with itself. This with itself. See, you get n for each one. The answer will just be n. In this case, since n is 4, it will be 4. If you want to do it really quickly, remember this is 1, 1, 1, 1, right? 1, 1, 1, 1. What is 1, 1, 1, 1 dot product with 1, 1, 1, 1? 4, right? So you'll see this will be true for all of them. And then you get 1 over n here. So why do you get this 1 over n? To normalize the entire matrix. Okay? And now we should invert this, right? So let's invert this. Its inverse is its conjugate transpose. First note that this matrix is symmetric. That's why we could read it off down the row and down the column. Same thing. Right? We could do that. That means this matrix is symmetric. That means that it's inverse. So look at what's going on. This vector stays here, it moves here. This vector comes here. That's what the inverse is, right? It's the inverse of take this, give me this. And how do you get the inverse? Well, just replace all these sort of powers with negatives. Okay? This is inverse FFT. This is the naive inverse FFT matrix perspective. Yes, this is the naive inverse FFT matrix perspective. My claim to you, and I don't have those on the slides because I knew that this is all I would be able to cover, is that the polynomial perspective of this is exactly the same. Just pretend like the 4 numbers in here, right? The 4 numbers in here is a polynomial, pretend, right? And do the polynomial perspective. And this is the same thing as the FFT algorithm. There is no difference. It's just that instead of evaluating them at the roots omega to the 0, omega to the 1, omega to the 2, and omega to the 3, now you're evaluating at omega to the minus 0, omega to the minus 1, omega to the minus 2, and omega to the minus 3. Everything else is the same. Does that make sense? Okay. So the inverse FFT algorithm is exactly the same, just with different points to evaluate at. That's the only difference. And a fun fact is that you know how you square the nth roots of unity and you get the n over 2th roots of unity? If you square the inverses of the nth roots of unity, you get the inverses of the n over 2th roots of unity. And that's why this whole thing still works. So these complex numbers of roots of unity are pretty magical. And this is our entire picture now. We've sort of filled in this question mark, which was we can take Rx in value form back now again in n log n time. And so this whole thing, well, here we have 2 polynomials, we're taking them. That takes n log n time. We multiply, takes n time, we bring it back, n log n time. And this is just a picture. P of x goes here, Q of x goes here, do the multiplication here. And then this gives you R of x doing the multiplication, and then take it back. This is IFFT, this is FFT. This is sort of the Fourier transform, this is the Fourier transform, this is the inverse Fourier transform. This whole thing is called the FFT. Okay? All right. Questions, I'll take them up ahead. Thank you.